Let's begin with a word of prayer. Dear Heavenly Father, we thank you for this day. We thank you for a semester nearly completed. Let's pray with us today. Help us to glorify you when we do this day, Lord. In your name I pray. Amen. So, the last thing on my list of topics was to talk about a little bit about the, let's say, the 2 square and 4 square identities. So basically, here's the deal. Well, tell you what, let me show you what it looks like in the complex. So in the complex numbers, right? If you look at the complex numbers, we have what? We have z equals to, say, x plus iy. You may have noticed my son is here today. Z equals x plus iy. And then we also have a conjugate. Z bar, right, is x minus iy. What happens? All right, let's see if I can remember this. It's debatable. Of course, if you take z times z bar, what do you get? X squared plus y squared, right? Let's see here. He's stealing all my markers. I better put some away while I still have a chance. Haha. Prepared. Let's see here. What if you look at, man, see the 2 square identity, it relates, oh goodness gracious. See, that's not it yet. That's part of it. Oh, here it is. So if you look at, well, let's see here. Let me just write it out, and let's see if we can discover how it comes from complex conjugation and such. The 2 square identity is specifically this. x1 squared plus x2 squared times y1 squared plus y2 squared the 7-year-old perspective on this class. Let's see here. x1 y1 minus x2 y2 squared plus x1 y2 plus x2 y1 quantity squared. So this is, hey, cut that out. The 2 square identity. So what we have here is a product of the sum of 2 squares, right? Written again as a sum of 2 squares. This is a 2 square identity. Now, if you've taken number theory, you've probably seen how this is useful for studying various patterns and primes and such. Can you see how this comes from complex number multiplication? Let's see here. What if we let z1, right, equal to x1 plus ix2, and if we let z2 equal to y1 plus iy2, right? What's z1 times z2? What's that give us? That gives us x1 y1 minus x2 y2 plus I times x1 y2 plus x2 y1. Okay, so what is this? I mean, this is what? This is actually This is Z1 bar, let's say, right? You see that? And what's this? That's Z2 times Z2 bar, right? And what's the other side? I don't know. The other side is Z1, Z2 parentheses, right? Times Z1, Z2 bar. Right? Because it's exactly the length of this complex number squared. In fact, what we're really looking at here, right, guys, is this idea that the length of the product of two complex numbers, and, well, specifically with squares, right? The length of the product of two complex numbers is equal to what? It's equal to the length of the first complex number times the length of the second complex number squared. And then, but, you know, z is greater than or equal to 0, hence what? Z1, Z2, the product, the modulus of the product is the product of the moduli. I told him to bring something to read. He has a backpack with an iPad in it. He has math homework he has to do before he gets home, otherwise he will not be allowed to do other things. But no, he will not bring those things. Anyway. Does he get missions? Not yet. All in due time. So this is very special, right? It says that the length of the product of two complex numbers, right, is the product of the lengths of the complex numbers which are multiplied. That's really, really simple, that idea, right? Can you repeat this? What if you take a vector space, right, of dimension n? Is it possible to define some way? I mean, let's try to be a little bit more abstract. So here's the abstract. Ah! Hey! You're like, that's what I wanted to do all semester. That's why my friend Somber Paul once left mechanical engineering because he was taking some course, and he told me that every day he went to class and he just really wanted to go up to the front of the room and just punch the professor in the face. He just it was all he could do to physically Uh-oh. So anyway, so Paul dropped his mechanical engineering major. All right, so here's the abstract problem. Can you do this for an n-dimensional vector space? Or how about just, or, you know, equivalently Rn? Is it possible to, say, define something, let's say star, which is a mapping from Rn cross Rn back to Rn again, all right? So xy maps to x. Let me just use an asterisk y here. Ah! Hey! Ah! I have videotape evidence of this. I'll show mommy later. So we want to make this a so-called multiplication on the vector space. What would you like from a multiple? If you're going to multiply vectors, like we multiply complex numbers, thinking of those two-dimensional vectors, what would you like from your multiplication? What should its basic properties be? Well, certainly we should have this, right? It should distribute across addition, right? What else should you be able to do? How about pull out constants? Anything else? Well, if that's all you want, good news. There are tons and tons of multiplications out there. Hundreds, thousands, millions, I don't know. There's just unlimited rules that you can define that, okay. See what you did there? Not bothered by it. All right, so, I mean, this isn't a problem. I mean, I can define all kinds of multiplications that are distributive like this, but, you know, there's something deeper here. Can you define a multiplication that behaves this way with respect to Euclidean length? Can you also, let's get greedy. You also want what? You want the length of x star y to equal to the length of x times the length of y. See, this restriction right here, this limits possibilities quite severely. It turns out if you want a multiplication on Rn, which distributes across addition and behaves as usual, all right? For example, if you want associativity, if you want an associative multiplication, would be what? X star y star z, x star y star z. If you want that also, then it's only possible to find such a multiplication in n equals 1, 2, and 4. That's it. So n equals 1 is the real numbers. N equals 2 is the complex numbers. We just looked at those. N equals 4 is the quaternions. You're like, what are quaternions? Quaternions are the real span of the number 1 and the imaginary units I, j, and k, so-called versors. The way they work is that I squared is j squared is k squared. They're all minus 1. And like ij is equal to k, but ji is equal to minus k. So what do you think ki is? What's k times I equal to? If you're sensing the pattern here. What would k times I be equal to? Yeah, just j. They behave like cross products. So, you know, a rather famous story is Hamilton looked for something like this. Hamilton looked for something like this in the 1840s in 3 dimensions for like 10 years, a long time. Just mulled over this problem and tried and tried and tried and tried. Not because he was originally trying to find a multiplication of numbers, I think. Actually, he was after, like, could you find, I better talk about it before it's too late. Could you find an analogous thing for, like, 3 numbers? See, because the length of something in R3 is what? It's something like x squared plus y squared plus z squared. I think you guys are an good influence on my parenting. You're bad influence. I'm not going to hire any of you as babysitters. Charge a high price. Anyway, long story short, Hamilton could not find this multiplication of three-dimensional vectors that behaved like this because, in fact, it's impossible. Correspondingly, there is no 3-square identity. But there is a 1-square identity. Oh, sorry, that's kind of boring. There's a 2-square identity. We just worked it out over here. There's also a 4-square identity, which comes from the fact that if you look at the product of two quaternions, it's equal to the, well, it's also true for the natural Euclidean length in quaternions that you can equate. But you don't want me to write this out. There's 16 terms. It's rather ugly. But there is a 4-square identity that comes from the fact that quaternionic multiplication respects the norm like this, the length of the vector. And there's also, actually, if you drop associativity, you can also get this property as well in the case of what are called octonions, which have these 1 plus 7 sort of versors, but it's a non-associative multiplication. But there is, in fact, an 8-square identity. And there's a long history of these things, and it's very interesting. But one thing I wanted to draw your attention to, just this much. No erasing me. If you are courageous, this is stated carefully. In fact, the 4-square identity, I think, is, yeah, there it is. It's on page 308 of your book. But Theorem 35.3 by Hurwitz in 1898, he proved the following, that the composition of sums of squares can have a solution only when n is equal to 1, 2, 4, or 8. And this naturally corresponds to whether or not there exists a natural multiplication on Rn. No, he jumps. He jumps. Yeah, but he jumps higher than I do. So. Anyway, the proof is rather explicit and given on page 309 to 312, 313. No, wait a minute. It's about 4 pages. It's rather long. I will not do it, don't worry. I just wanted to mention these fun facts to you. So with that, are there any questions about the final?
Everything. Can you just teach the whole class, like, again?
Everything.
Teach the whole class again today?
Yeah.
What do I?
If I die during it, will you write a letter of apology to my parents?
There will be no dying. Daniel, fine. You want to go there? We can go there. Daniel, no hitting me. So, no, I cannot reteach the class today. I mean, shockingly. How about this? Yes. Have I? Yes, the final from yesteryear is posted.
Is it on your?
It's in the course content. It's like under, what is it under?
Like on Blackboard? Or
Yeah, it's on Blackboard. Course content. Maybe it was that email I sent out like a couple days ago, the link.
Oh, is that what that was?
Yeah. Here's one question. Here's one fun kind of question. Something I raised earlier in the course, right, was suppose so here's a question that we found rather vexing earlier. I think we could answer easy now. Find system of equations which has 1, 1, 0, 0, and 1, 2, 3, 4 as solutions. It wasn't quite the question we asked. I mean, there was something like that was the question we asked, right? So this inverse question of, how do you find a system of equations which, okay, how do you find a system of equations that has a particular pair of vectors in its solution set? So you guys have any ideas? I mean, you're looking at what kind of, you need at least how many columns to make this sense? 4, right? And so, I mean, I guess you're just looking at something like A1, A2, however many equations you need, say AM, right? Times, what do you want? Well, you want 1, 1, 0, 0 to be 0, right? The same for 1, 2, 3, 4, right? What is that, though? What is this kind of multiplication? I mean, what is this really? This is nothing more than like A1 dot 1, 1, 0, 0 and A2 dot 1, 1, 0, 0 and so forth. Let's say it's A sub I dot 1, 0, 0, 0 equals 0 for all I, right? And you also want AI 1, 2, 3, 4. So what is this problem? I mean, you're trying to find equations which take, Daniel, stop. What is this? Did you find that under there? Was that just under there? Here, make it into a paper airplane. Do something useful with your time. There you go. Okay, so you're trying to find a system of equations which has that as the solution, right? That's equivalent to trying to find vectors which are perpendicular to those two given vectors, right? So we have a method of calculation for this now, don't we? We just need to find what? Basically, the perp, right? So we can actually just look at 1, 1, 0, 0, 1, 2, 3, 4, and try to row reduce this, right? So in other words, I'm trying to find basis for S perp with S equal to this to what? Remember, we learned that what you do is take those vectors, transpose them, and row reduce them, find the basis for the null space of that transpose matrix, right? And that will be it. So let's see, row reduction.
0, -3, -4, 0, 1, 3, 4.
The upper ones.
Oh, you're just.
That was the whole.
Oh, you're one step beyond me. Okay, so. Okay, so what are we looking at here? Something like, so if basically if A1, well, if AI is equal to what? AI1, AI2, AI3, AI4, right? if that's your ith row, what's the condition that you need on that? For these to appear as solutions, what's the condition we need? We need what? We need AI1 minus, so equals to what? Equals to 3 AI3 plus 4 AI4. And also we need what? We need AI2 equal to what? Minus 3 AI3 minus 4 AI4. There are infinitely many systems, right, which take those as solutions. You pick any which ones you want, right? How about we'd like a non-trivial example. So let's try for what? How about AI3 equals to 1, AI4 equals to 1? What does that give us? So in total, we get what? We get something like 7x1, right? Minus 7x2. What? Plus what? Plus x3 plus x4 equals to 0. This equation has these two as solutions. But if you follow my calculation, you can easily generate many more equations which are interesting and not looking the same as that one, which still possess these two vectors as solutions, right? Because finding a system of equations which has those vectors as solutions is equivalent to finding the perp to that space, which is a problem that a lot of you had problems with. Yes, which is why I'm going over this. Let's see, what else could I tell you guys in a short time that might have an impact? I think a lot of you don't know what composition of operators means. From what I see on the test, you think that tx cubed is equal to t cubed x cubed or some such nonsense. This is crazy. T cubed is meaning composition of t 3 times. This is an operator. When we talk about squaring or cubing or even inverting an operator, we're talking about with respect to composition of functions. What'd I do? Oh, you're just talking about it? It's cool. So what I did was I just put, first of all, I decided I don't really need a bunch of them. So you just set I equals to 1 if you want. We just need one equation will do it. This has infinitely many solutions, right? Any choice of AI3 and AI4 will do. So I just pick both of them being 1. That makes this be 7. It makes this minus 7. So what are those? In terms of the system of equations, you have like A11 x1, right, plus A12 x2 plus A13 x3 plus A14 x4 equals to 0. We're looking at a homogeneous problem at the moment. So then that's just 7 minus 7, 1 and 1. But you can easily choose. I mean, if I'm not careful, there's always the stupid answer. I give you the 0 equation, it has them as solutions, right? Because the 0 equation has all of our 4 as solutions. So it's surely, I mean, hopefully if I was to ask such a question, I would be careful not to allow you that luxury, logically speaking. Yes?
What was that proof that you said no one could prove last year if you didn't get it?
Now, last year, many people made A's, but like 2 years ago, no one can prove that the if U and V, well, say U and W are subspaces of a vector space V, then U intersect W is a subspace of V. Like, there was a whole class that couldn't prove that convinced me that they shouldn't earn A's. Because it's like just straight subspace test, which by now you should know cold, right? Subspace test. Yes. I mean, the proof that the intersection is a subspace, how about this? 0 is an element of U, and 0 is an element of W because they're subspaces. Therefore, 0 is an element of U intersect W. which is not empty, right? Also, if you pick x and y in the intersection, then and see something in the field, then of course cx plus y is an element of u. X is an element, x and y are elements of u, and x and y are elements of w by definition of intersection, right? So then what? So cx plus y is an element of u, and cx plus y is an element of wy. Since they're subspaces, right? So they're closed under addition and scalar multiplication. And then, by definition, which says what? Cx plus y is an element of the intersection, right? Hence, u intersect w is closed under addition and scalar multiplication, and is hence is thus a subspace by the what? Subspace test theorem, yeah. Anyway. All right, getting back to a more salient point. This here is something you guys should know. Like, whoa, catching. So question 1 on test 2, right? You've t cubed. So I gave you that x was an eigenvector with eigenvalue 2, right? Most of you got that, which is great. That is more than I can say for some classes. People have this ability to resist learning the definition of what an eigenvector is. You guys have overcome that. Congratulations, that's good. That is a good first step. Most of you, I think all of you maybe, knew this. And that is actually a significant thing for the class. I'm not being snide or anything here. Do you want to play with the iPad today? Because I can take it away. Even though I don't even like to play with it. Cease. All right. So t squared of x is what? This means t of x, right? Which means t of 2x. Because x is an eigenvector with eigenvalue 2. The 2 pulls out because t is homogeneous, because it's linear. That was given. And then you get that this is what? That's why it's 2 times 2x. Some of you claimed this, but you wrote things in between that indicated a deep misunderstanding of what the notation means. All right? There's only like maybe 4 or 5 of you in here who actually did this with understanding. That concerns me a little bit. So there's one thing. Composition of operators, multiplication of an operator is composition. Okay? This is kind of an important point. Yep.
Do you think that the final will have more questions like test 2 since it?
The final is comprehensive. It will have test 1, it will have test 2, it will have quiz 1, it will even have some quiz 2, not too much. But I would like to ask a question, hello. Here, let's look at, where was I?
If you were to approximate the percentage of groups versus computational, what would you approximate?
I would say that you need to learn, what's going on here? I don't,
Proofs and like the stuff for test 2 that didn't show up on test 2.
there's a lot of,
Proofs in the notes and whatnot that didn't show up on test 2.
such as,
I don't know,
Such as?
You want like a specific example?
Yes.
8.3.7.
8.3.7.
Pretty good chance that's, I don't know. Really, any of the proofs in any of those chapters. 6, 7, 8, 9, 10. 7, 8, 9, 10.
Now, in terms of the quiz 2 material, though, I'm not saying that's going to be a big part of the final. That is actually a very small part of the final. But I would like to at least have a token question on possibly minimal polynomial and how to read. I think a lot of you would like to be tested on how to read the minimal and characteristic polynomials from a Jordan form which is given. Yeah. Yeah. So, right. I don't know why I'm going to this one. No, I don't know why I'm going to this number you randomly made up. I'm not sure why I'm actually doing this, but I mean, can I test all possible proofs on the final? No, I don't think I can.
Is there any sense of which ones are important to you? There's
Ironically enough, this is actually a very important one. So much so, I was just going over it. So yes, that one does matter, I do think. Because if I ask anything about how to find the basis for an orthogonal complement, this is the go-to theorem, right? Now, you guys, just because you can do the Gram-Schmidt algorithm doesn't mean that you have to. I did not say find an orthonormal basis on that problem on the test. I said find a basis for the orthogonal complement. Some of you did that and then proceeded to start running Gram-Schmidt on it. No, there's no need for that. I didn't ask for that.
They're more convenient.
I just want to show you everything that I can do.
Yes, but I would much rather see you spend time to show me that you know how to do one of the proof questions later. Don't answer that. Don't answer that. Don't answer that. I'm trying to give you the academic Miranda rights at the moment. Let's see here. Just let's see here. Look, let's see here. Let's take a stroll back down memory lane. What did test 1 look like? Remember test 1?
No.
Oh, you'd rather forget? That's probably not a good approach to take. Listen, if you think about the extra EML stuff, a lot of that doesn't matter. All right, that's true. But there are some things that you should try to understand, like what is the minimal polynomial? What is the connection of the minimal polynomial to the problem of diagonalization? I actually do care about that. Can you guys tell me quickly what is the connection between the minimal polynomial and diagonalization? What's that? A matrix is diagonalizable if and only if what about the minimal polynomial happens? The geometric and algebraic multiplicities equal. True. I believe that's true. Yeah, that's true. What's that? They have to be one. Yeah, the minimum polynomial has to be a product of linear factors, not repeated. That's diagonalizability at the level of the minimal polynomial. Right? That's the big thing. Yeah. And also just the connection between the Jordan form and the characteristic and minimal polynomials, which you guys just mentioned. Yeah.
So like on most of the tests, there's like this like cusp on the proofs of like if it's like 2 pages, it's probably not a thing. But on the final, would you find yourself doing like a question that would be like a 3-page proof, or can we still safely assume that probably
I'm not sure that there's really any 3-page proof we've done in here except for the one. The replacement lemma. Yeah.
So like in the past, you've given us the advice of like, if it's a really long proof, it's probably not going to be at a test because
it takes
time
an hour.
is a thing.
Yeah.
Does that rule go out the window for the final,
I think that well, listen, you guys, like, I mean, for the final, I really need something to decide my C's from my D's more than I need something to decide my A's from my B's. So, you know. That's not what that means. That's not what I meant. You know, don't forget there's things I said earlier that I tried to get across to you, but then try as I may, they never quite sink in before the test. Like, if something's a span, how do you show it's a subspace? You go, it's a span. So it's a subspace, because a span is by definition the set of linear combinations which is closed unto itself. Yeah. No. No. There's no. There's no notes. No notes for the final. That just gives you a false sense of security. It actually doesn't help you. It actually hurts you. I know this from previous experience. Do you understand linear extension? Do you have a clear mind on how to find the matrix of a linear transformation, you know? Do you know your way around the real spectral theorem? I think a lot of you seem to know something about it from what I saw in the encore part. Like, not bad. I think generally speaking, the class did pretty well in the quadratic form questions. Some of you. If I say that vectors are really, really interesting, why are you ignoring them? Why? So many of you guys were like trying to calculate the characteristic polynomial, that 3x3 matrix. That eats mounds of time, right? I mean, determinant of a 3x3 matrix, factoring a cubic. Ugh. I mean, if you got no options, then fine, but I gave you vectors. And I said they were interesting. Why ignore that? I'm not acting against you. I'm actually interested in you doing well. If I give you information like that, it's not some kind of cruel trick. Those were eigenvectors. All you had to do was multiply a matrix, and you'll get back the vector again, and you go, aha, eigenvalue blah and blah and blah, and you're done. No calculation of characteristic polynomial needed. Just because you can do it doesn't mean you should. You must think before you calculate. All right? Yeah.
Will the solution to test 2 be posted, or has it been posted?
Is it already? I think I posted it. It's.
Can we get ours back?
Yeah, I'll give you your test back here in just a second. Oh, I know. No, I'm not posting the solution to last year's final. I just posted but come on, the questions are not that tricky. Yeah.
Will you have anything on tensor products?
Will I have anything on tensor products? That might happen, yes. But the simple stuff, yeah. There were like 5 problems in the homework. It would be like those, something like those. But we're talking about second order or third order considerations for the final. Like first order considerations are test 1, test 2, and the routine homeworks, let's say. Quiz 1 also, of course. I hope to have quiz 2 done sometime soon. So, hey, what? Do not endorse this message. How dare you, sir?
As far as determinants go, like some of the things in like proofs of some of those are like kind of lengthy for like various parts of it. Using like what's.
Oh, I don't think. I will. I mean, I don't rule much out, but I think proofs on thing. It's probably not the case that there's anything in the determinant chapter proof-wise that I would ask about. At least like in terms of like the product of the determinants being the determinant of the products. I don't think we even did that in class this time around. I want you to know properties of determinants, right? But I mean, for example, proof of Cramer's rule I don't think is that interesting. We have 2 hours for the final. There are more important things. Yep.
Isomorphism, the first isomorphic theorem, probably good to take it, I could say that.
Yeah, I think it would be good to know the first isomorphism theorem and, you know, perhaps its proof. Some of you proved the second or the third isomorphism theorem on the Encore, from what I saw, but no one checked well-defined. Okay, you might have. I'm at least a couple of the ones ones I do remember. Maybe I don't remember yours, but a couple of the ones I remember didn't really check the well-defined issue. So you might think about that a little bit. But again, I feel like that's second order for the final. Like first order, you want to do well in the final. You need to go make sure you know how to do row reduction. You know column space, how to find the basis for a kernel, what the dimensions theorems say, how to apply rank nullity to a map, how to find the matrix of linear transformation, the basic stuff. You know, it's gonna be a lot of that. I guess I should give you back your test.
So when did you go to sleep last night?
What's that? Me? Sleep? I wish. See here. Hey, you want to give these back? You can cut off the...